In this video, we'll be describing what diffraction is and how it applies to thin slits. Now, diffraction is basically the effect where light will spread out as it goes through a small hole or around the edge of an object where the light has been blocked. Now, it can be understood in terms of a wave effect through Huygens principle. Now, here what I've done is now superimpose the wave fronts of light, whereas before I just showed the rays. Because if I look at the rays, this doesn't seem to make a lot of sense. We talked about rays continue on a straight line unless they meet an interface where it changes speed. As it goes through the hole, it never changes speed, so the light ray shouldn't be bent. This is not refraction going on. This is a new effect. And if you just simply looked at the ideas behind geometric optics, the idea is that the light ray would just continue straight through, and whatever light rays hit this surface would be stopped. But where there was a hole, nothing special would happen. It would just continue in a straight line. However, the wave fronts will indicate that something special happens. Now, the idea is that these light rays propagating to the right. In this picture, we imagine a light source that's far off to the left, so the light rays are moving in just from left to right, which would be a rightward arrow, or arrows for the rays, and vertical wave fronts. You can imagine these being like the waves from the ocean coming into shore. But as they go through a small hole, Huygens' principle tells us that the wavefront is essentially the same as putting a bunch of small wavelets caused at that one point. Like if you were bobbing up and down a bob in water or a stick in water, you would send out spherical ripples. Now, if you do that with a bunch of things all in a line, they make a long crest, like this side. But if you block most of them, what you find is that the rays, the light coming out from that small hole, or if you imagine this as a water wave, the water waves coming out from a small hole will go out in all directions. So Huygens' principle suggests that for waves, it'll spread out if you block the waves on either side, like here. This is a new behavior for light that we haven't talked about yet. The confusing thing is that it sounds very similar in its terminology to things we have talked about. We've talked about two effects so far, reflection and refraction. We are now adding diffraction as a new effect. So let's clearly describe what each of these things are so we don't get confused. Reflection is when light stays in the same medium, bouncing off of an interface where it changes speed. Refraction is where it crosses into that new medium where it changes speed, and we use Snell's law in that case. It'll get bent unless it hits exactly perpendicular. And diffraction is how light spreads, not as it crosses into a new medium, it's staying in the same medium, but it goes near an edge or a hole in a barrier. Now, the first two can be understood purely using the rays, and diffraction really can only be understood by discussing light as a wave. And let's talk about what would happen if we had two slits, because right now we only talked about what happens if I have one, and it spreads out. Okay, so it's going to become more sort of diffuse as it goes out through a hole. If I thought about this purely in terms of rays, I had a light source with two slits, and then a screen that I was going to look at this light source through the two slits. I would expect to see light rays coming through the top slit and through the bottom slit, making a pattern on the screen. Effectively, I would see the shape of those two slits projected onto the screen. Just like if the sun is shining through your window, you see an illuminated area on the floor in the same shape as the window. That light shines through where it can, and where it can't gets blocked, and then the illuminated area has the same size and shape as the slits, the thing that lets the light through, which is slits in this case, or your window at home. And this is a pretty good model for discussing what happens for large slits, but this isn't what happens for thin slits. Instead, you see something like this. So in this video, what you're going to see is what happens when you get two different wave sources. And I can show you and you'll see what happens in the light case, but it's not really easy to visualize light as a wave because when you see light, you just see light. But if you see the same effect in water, you can get a pretty good idea of what goes on. So here's a pond, and they're going to, the author of this video, this is Verasium, who has some pretty good physics videos, by the way, if you're interested, on YouTube, is going to do a demonstration where he bobs up and down and then sink two different balls. And these small balls will create circular waves. And as we said, if we had two wavefronts passing through two small holes, Huygens' principle would say that we'd create waves just in the same sort of way. It was as if we were bobbing up and down on water at two different points, which is what he's literally going to show you. And we want to see what happens with the resulting waves. So he's going to start bobbing them up and down. And as you can see, when you have a single wave, bob one up and down, you make these really nice circular wavefronts that come out from just that one object. We want to see what happens when we have two of them. Notice what it looks like in here. You can see these crests, but not along these strips here. So it seems like there's bands where there are wavefronts, like out here, and then bands in the middle where the water is still, that it is flat, so you don't see this banded stripe, which is indicating that there are wavefronts here. The water along here, and there, and there, and there, and there are all sitting still. Whereas in the middle, it's actually moving quite a bit. I'll show you that again. And just take a look and see that some points are sitting still and some points are moving up and down. And he's going to point this out in this really area, point out that where the light is sitting still in the water will correspond for light to where it's dark. And the regions where it's moving quite a bit is where it would be bright. In between there. So what would we expect if we shined light in a similar way? We would expect that there would be bands of dark where the wave is not moving, and then there will be bright areas where the wave is moving quite a bit. You would expect something like this to show up for the wave. But we want to say what will happen if you look at a screen. So imagine the screen was at the top of the page. You would actually see the light as it traveled from each of the slits to the screen. All you would see is the light on the screen. And what you would see is bright, dark, bright, dark, bright, dark along the top, which would look something like this in my picture, where yellow is where it is bright, and the middle is where it isn't. In other words, you see many, many bars of bright, then dark, then bright, then dark. So the question is, what do you actually see in real life? Do you see light as the two, as kind of the shape of the slits themselves, those two bars that would sort of match what you see when you look at a window? Or do you see something like for waves where you get many, many, many bars? And I'll show you an actual demonstration of this. Now, let me just start the discussion in this video by showing you what's going on with the physical apparatus. This is another video by MIT demonstrating this effect. What you have on the left side over here is a laser. that laser is shining upon two very narrow slits. What they're showing you in this inset is a pair of slits that are so close you can't even really see the separation between them. This is actually very closely spaced slits, slightly less, and then slightly less spaced slits. And where they're shining is right in this case. Here you can actually see there's two slits side by side. Here you can't, but that's just a question of the resolution of the video. Now, what they've done is they've blocked one of these slits with a laser. So you just have a single slit that is the source of the waves. It's coming out, so the laser is hitting that slit, and then the laser light is hitting a screen over here. They have a little webcam that's taking a picture of what it looks like, and they're showing that down here in the video. And what you can kind of see, again, this is a little bright, so you can't see it very well, is that you get a broad smeared pattern on here. And the reason why is because as it goes through a single slit, it gets split out by diffraction. And so what we find is a kind of smeared out region of light. Now this shape here is not in this, it is actually horizontal, and the slit itself is vertical, so it's not in the same shape as the slit because there is this diffraction going on, this spreading out effect as it goes through the narrow hole. But the question is, what happens if you have two slits? If it's ray-like, you would expect to see two bright dots, basically, one from each of them. If it's wave-like, you expect to see many bright dots side by side. And they're going to show you what happens when you uncover the other slit. Here is the actual inset where you can see the razor is blocking one of the slits. He's going to move it. And what you see is many, many bright and dark patterns, which is what you saw in the case when you had water waves being made side by side. Here, dark, bright, would correspond in the water to being kind of thrashing up and down water, still, thrashing up and down, still, and so on in a pattern. So this effect is very, very wave-like in its nature. And in fact, it was one of the original proofs that light was a wave. This is a much more detailed picture of that same effect. Here the contrast is a lot higher. This is shot in a dark room as opposed to a well-lit room. So you can be able to see these bright and dark bands show up much more clearly. And what I mean by that is bright, dark, and so on. When do you get this effect? Because you don't always notice this effect. Now, there's a couple things you need. One, to really see this, they have to have the same wavelength. All the light that's shining through there is the same wavelength, aka it's the same color. So this is why we're showing a very distinct red. It could be a very distinct blue, it could be green, it doesn't matter which color, but it has to be one color. White light looks different through here, and we'll talk about what white light looks like, than if you just have a single color. Now, the other thing is that it has to be coherent. Now, what that means is that the light wave fronts that pass through each of those slits have to be in sync with each other. So that means that it's you're going to be equivalent of bobbing those balloons up and down at the same time in the water. In real life, what you sometimes find is that the relative timing of those two sources varies over time. It's kind of like they kind of move in and out of sync with each other because the light at one spot is not exactly the same as the light at another spot. That they're a little bit different at different locations. So you have to have this. It's kind of maybe slightly confusing terminology, but you have to have this additional condition that they're coherent. Essentially, they're doing the same thing at each of the slits in order for this to work. And the third condition is actually really a statement of the first one. Again, note that lasers satisfy these conditions very easily. So if you point a laser pointer through two small slits, you will notice this effect.